Good afternoon. In this video, I will present the new SBeXpress module, the Parametric module. The Parametric module is essentially an extension of the detail object. It assigns parameters to the drawing elements inside a detail object. And when those parameters are modified, the graphic representation of the detail object is updated accordingly. The Parametric module commands can be found in the VB Formwork ribbon area. There are two groups here. The first is the Parametric Detail section, which contains commands specifically related to the Parametric Detail object. Of course, editing the detail object itself works in the usual way. The second part is the Parametric Library section, where, besides the built-in node details delivered with the program, users can also insert their own custom details. Let us begin with a simple object, a column. With this command, we can insert an object, and the function immediately opens the parameter dialog. The parameter dialog can be docked to the left or right, and its structure can be divided into two main parts. On one side, there is a parameter table, which contains the parameters assigned to the detail object. It may also include program code with instructions that the software executes when updating the given parametric detail. This is a relatively simple detail. A rectangular column starting from the slab and supporting the slab above. It has a width and a depth, 4 longitudinal bars in the cross-section, and stirrups that can be densified at the bottom and top. There is also a story height, 2 slab thicknesses, a lap splice length, and a level marker. I will only mention parameter creation and code creation very briefly here, because there will be a separate video about that. The important point is that constraints can also be assigned to individual objects. For example, a dimension line can be constrained so that its 2 points always belong to a given segment of a contour object. Another possible constraint is that the y-coordinate of a level marker always matches the y-coordinate of a certain point on a contour object. Stretching constraints can also be created, for example, so that the lower line of a ladder object always stretches to a given edge of a contour object. It is important to know that these are always polylines, and it also matters exactly which point of which polyline the constraint is attached to. If auxiliary graphics are enabled, the program shows in a faint color which constraints are assigned to each object. In this example, dimensions and level markers are constrained. In the parameters section, parameters can be organized into categories. Each category can be expanded or collapsed in a tree structure. Parameters can have different types. For example, the column label is a text type. There can be integer parameters and geometric size parameters such as width, depth, and height. There can also be real number parameters, such as the elevation value of the base level marker. Reinforcement-related parameters are also possible, such as stirrup diameter and spacing or longitudinal bar diameter. Again, I will only discuss parameters very briefly. With this button, we can review and modify them. All parameters are listed here. New ones can be created and old ones can be deleted. Every parameter has a reference name. For example, the column width is the X dimension. This name is what we use in the code section when we want to refer to that parameter. A default value can also be assigned, and the parameter type can be set. Available types currently include horizontal distance, vertical distance, general distance, real number, dimension in meters, centimeters, or millimeters, integer, text variable, reinforcement, enumeration, and angle value. As mentioned, parameters can be assigned to groups, and the group name appears as the header here. A description can also be given, which the program displays next to the variable name. Minimum and maximum values can also be assigned, and the program checks them when values are entered. If an entered value is outside the permitted range, the program corrects it. A dimension can also be assigned to a variable. For example, this dimension can be assigned to the width parameter, and I will show in a moment why that is useful. We can also assign an owner. If the width parameter clearly belongs to this rectangle, then the rectangle becomes its owner, and whenever the parameter is modified, the rectangle width changes accordingly without requiring explicit handling in the code. That is all about parameters for now. As I said, each parameter has an associated dimension, so when a parameter is modified, this little diagram helps immediately. When I select a field or row, the program highlights the corresponding dimension, so we can see right away that this one refers to the column width. We can type in the parameter value directly, or we can indicate a line in the drawing. The small icon shows whether the parameter is a horizontal length, vertical length, and so on. Whatever parameter I click, the program highlights it in the drawing. The same applies to reinforcement parameters. If I click the longitudinal bar, it is immediately highlighted. For reinforcement parameters, there are 3 buttons to change values. One opens the reinforcement dialog, which contains the full longitudinal bar settings. Another allows a simplified diameter and spacing setting. For longitudinal bars, spacing is not really applicable, but for stirrups it is. And there the spacing value is displayed as well. The ladder object can also be modified here if something special is needed. But in general, this button for changing diameter and spacing is sufficient. This detail object is built from contour objects. Anyone familiar with the formwork module already knows what that means. For example, this is also a contour object with an empty fill. Although it appears to consist of 4 separate lines, in reality it is just a contour object with a dashed line type set at the 2 edges. If I switch it to a normal line type, it becomes immediately clear that it is a square. A contour object has a contour style where color, fill, and various other parameters can be set. It is also important to know that contour objects can be named using object identifiers. For example, I can call this contour object AF, and then everywhere in the program where I want to do something with it, I can refer to it as AF. There will also be a separate video about that. Still, I can briefly demonstrate how the editor works. At first the code may look complicated, but in fact it is not. If I type E, that means I want to do something with an element. When I type a dot, the program immediately lists the available elements, and I can select AF from the list. So with E.AF, I have told the program which element I mean. If I type another dot, the additional parameters I can modify appear: width, height, center point, upper plane, lower plane, left side, right side, and so on. P1 or P2 obviously means point 1 or point 2 of the polyline. If I continue and set x equal to, say, 76.1, then this instruction means that among the elements, the x-coordinate of point P2 of object AF should be equal to 76.1. With the buttons below, I can run the code. One runs only the selected line, another runs the full code, and if auto mode is enabled, the whole code is run automatically whenever any change is made. Now I only want to run this one line, and it is visible that the point has moved. I did this only for demonstration, but the editor helps in the same way even when it's not a simple assignment. It does not have to be a fixed number. We can refer to parameters, reinforcement properties, and almost anything else. There can also be instructions other than assignments. For example, if I type C for command, the program lists what commands are possible. If I type group and open the parenthesis, it immediately shows in the help tooltip which parameters the group command expects. Similarly, for mathematical functions, it also lists the available options. All of these can be referenced in formulas, assignments, and so on, but there will be a separate video about that. Now I undo the rectangle modification and delete that line of code. With auto mode turned on, everything updates immediately. So let us assume I start modifying the parameters. Width 40, depth 60, clear height 2.60, base level 2.35 meters, lower slab thickness 20, upper slab thickness 22. I can see the result immediately. Whatever I change is updated at once. Obviously, the predefined nodes I create may not suit everyone in terms of reinforcement or appearance. But because everything is controlled at the style level, it makes sense to adjust the display in our own drawing by setting the assigned style the way we want it. If that is still not enough, we can modify the node and then save it as a user detail, which can later be loaded just like the so-called factory details. For the longitudinal bars, we can define the overhang, the splice length, and the offset value, which can also be 0. There is an interesting IF section in the code that decides whether the bar should be straight or offset, depending on the offset value. We can also define a stirrup densification length. Within that length, the spacing is reduced to half, although this too can be changed in the code to anything we want. Here it shows 5 bars at 12 spacing, 9 bars at 20 spacing, and 4 bars at 12 spacing at the end. So the real goal of these parametric details is that nothing should have to be modified manually with Ctrl+ right mouse button. Everything inside the parametric detail framework should be defined and controlled through these parameters. Any additional modification should be updated either through constraints or through code. Let us look at another parametric detail, for example, this socket foundation. This one is already a bit more complex in terms of reinforcement. At the neck of the socket foundation, there are 4 stirrups lying in horizontal planes, while on the outside there are vertical stirrups. The horizontal stirrups extend down to this part of the socket neck. The lower slab is reinforced in both directions with U-shaped bent-up bars, and the reinforcement of the socket neck stands on these main bars. Here too, we can modify the parameters. Let me copy the whole thing so that the difference between the two objects can be seen. Whenever I insert a detail object from the library, it is selected automatically. This thick frame means that this is the object we are currently working on. If we want to change which object we are working on, we can do so with this command. Let us also look at a third type of detail: base plate reinforcement. This describes a situation where there is a base plate with lower and upper slab reinforcement, and at a recess, sloped offset bars have to be created. The interesting thing here is that trigonometric functions are needed for the calculations. For example, I use the tangent function, which refers to the angle. If I change the angle here, everything updates automatically. The column x dimension and y dimension work exactly the same as in the previous examples. So the purpose of the whole system is to let us create standardized reinforcement even faster. Obviously, a slab cannot really be standardized, but many tasks such as stairs, columns, retaining walls, and many other elements can be handled with these parametric details. If we have a well-organized library, we can create the required variant in the floor plan in moments. Thank you very much for your attention.